Okay. With Deborah's indulgence, I wanted to just take a minute since we're starting discussion sessions now. For the first time during this meeting, I wanted to explain a little bit where these discussion sessions are coming from. In part, we heard from many people that Zoom meetings are inherently challenging, and we agree entirely. You can see in the schedule, we've sprinkled breaks throughout, some quite long, hopefully to give people some time away from their computers and away from Zoom. And also we've, as was explained in the registration forms, which you all filled out several weeks ago, so I'll briefly repeat, we have chosen to give priority in terms of presentations, contributed talks to early career folks so that they have some visibility in the collaboration. And instead of having session after session of presentations with slides, we've prioritized discussion sessions. There are two types of discussion sessions, so-called hot topics and cross-working group sessions. The hot topics are themes that are relevant to the entire collaboration, not generally specific primarily to a few working groups. And they're hosted by one person with help from a Q&A manager. The one host is not necessarily presenting the whole time, but setting the stage for the discussion with perhaps a few minutes of context and introductory material. And then we encourage everyone to participate with questions, comments, and discussion. The cross-working group sessions are intended to be a little bit more focused, but still relevant to everyone, with the focus being to bridge gaps between working groups to make sure their interfaces are clear and to establish good communications in areas that overlap multiple working groups. For these cross-working group sessions, we have identified certain panelists who represent the different working groups that are involved, but that in no way means that other people should not jump in. The panelists, again, are there to provide context and background information and to seed a broader discussion. So please, everyone, feel free and take advantage of the opportunity to ask questions and participate. So that's all I wanted to say. Deborah, if you're ready and online, in my current view, doesn't show that you are, but
I'm here.
Wonderful. Please go ahead. Thank you.
Great. So I'm going to share a screen, and I have a few slides, which hopefully won't take too tremendously long, and then we'll have lots of time for discussion. So, okay, so I'm going to provide a little bit of background about data combination, and I've called this little mini talk "Telescopes and Pipelines and Collaborations." Oh my! So I think one of the things that can be difficult to get a sense for is what is data combination, and why is this a thing that takes up so much of our time and energy? A priori, it seems like this should be fairly straightforward. And indeed, the concept is pretty straightforward. We are combining the data from different data sets. So this is an example of an early DR3 pulsar, where each of the different colors is the residual plot, residuals in microseconds on the y-axis, time in years on the x-axis, and each of the colors represents a different PTA. And so the idea here is that data combination is exactly what it sounds like. You take different data sets from different telescopes or different PTAs or different backends, you bring them together and you create one complete data set. And the reason we do this is because the power of our combined data sets, whether that be different telescopes within NANOGrav or the different PTAs within the IPTA, is greater than any of the individual data sets. We have better cadence, we have better duration, we have more information, we have more frequency range. We just have a better data set when we bring together all of the data we have access to. However, this is hard. And the question you might ask is, why is this hard? Because it seems like making this plot should be easy. Like I just load in all the data sets and I run the pipeline. And what's the problem? Well, there's quite a lot of subtlety. Now, one thing that's important to understand if you're not a pulsar timer is that every time you add additional data to the pipeline or to the data set, you do have to rerun the whole thing. You have to reset your whole timing. You can't just use the solution you had before and move forward. So I can't just add some new TOAs to the TIM file and pass the same PAR file and the new TIM file off to the gravitational wave group. Every time I add more data, I do need to rerun the timing pipeline. And when I do this with combined data sets, I often find problems or challenges. So one challenge is just the sheer amount of data sets, especially in the IPTA data set. We're dealing with a lot of different pieces coming together, and each one of them can have individual challenges. And we also just have a lot of TOAs. Another challenge is a lot of different telescopes. So within the IPTA, we have about a dozen. Within NANOGrav, our big data combination challenge coming up is CHIME. And each telescope behaves a little bit differently, uses slightly different conventions, uses slightly different ways of approaching the process of creating times of arrival or of observing pulsars. And so every time I add a new telescope to my data set, I have to consider a whole bunch of new variables and a whole bunch of new challenges that are related to the fact that this is a different telescope. This is a different set of a different way of approaching the problem. Even though we're trying to do the same thing, we do it just subtly differently. And when we try to combine our data sets, those subtle differences become big challenges. Another challenge, especially on the IPTA side, is we are working with two different timing softwares. We're using both Tempo2 and Pint as our approaches. Another thing I didn't put on the list, but is somewhat related to this, there are many, many different ways to define a TOA. I count something like 5 different definitions of what wideband timing is among different groups. And you know, in the long run, we'd like to move towards a scheme in the IPTA where we have people submit their profiles and we make the TOAs for everything, which is going to bring a whole bunch of other new problems. But right now, we're taking everyone's final TIM files and bringing them together. And this can be challenging because how exactly is a TOA created varies between the different observatories, between the different PTAs. So there's a lot of different, and you know, it's hard to say a priori what all of these the problems this brings about are going to be, but they can be quite subtle. Another challenge is that there's a lot of people involved. And this is a great thing. I'm so glad that there are so many people who are excited about data combination. But there's also a lot of different opinions. And one of the things that's challenging with dealing with a dispersed team, particularly on the IPTA side, where it's very hard for us to all be in a room together, even virtually, is, you know, that a lot of people, everybody has their own opinion, everyone has their own prioritization. And one of the challenges of creating a combined data set is figuring out who is going to quote unquote win, whose way of doing something is what we're going to end up doing. And who is going to have to say, well, I really wanted to do it X way, but it seems like the consensus is Y, so we'll go with Y. And there's, you know, in leading a data combination, there's a certain amount of killing off your own ego too, and saying, you know, I have my opinions, but I can't just impose the way that I want to do the data combination on everybody else. So good news, bad news. The good news is every time we add more data to our pulsar timing array sets, we learn more. We learn more about our pulsars, we learn more about our instruments or our telescopes, and we learn more about our software and methodology. This is one of the best ways to learn more about the pulsar timing side of pulsar timing array science. Not only does it make our gravitational wave data sets better, it also teaches us a lot about what's going on in our pulsars, what's going on in our systems. You can learn things by comparing your system to another system that you would never know if you only had that one system. So if I only ever look at CHIME data, there's tons of things that I could be learning by comparing with GBT data, but we'll never find out because I'm in that one ecosystem. Unfortunately, that also means that every time we add more data, we learn more about our pulsars and our instruments and our methods. And that often brings new problems we didn't even know we had. So here's an example of one that I think is getting close to being resolved, but has been the work of several months. This circle here is around the purple data is showing the NPTA data. And the x-axis here is now frequency versus the y-axis is residual. And what we see is we see a definite frequency-dependent slope in the residuals from the NPTA data. You can also sometimes see it in the Meerkat data, but it's a little more subtle here. And what this turns out to be is it's related to profile creation and how the different TOAs work. And what we have to do is add a frequency-dependent, we have to add an FD jump. So we have to have offsets in our frequency-dependent parameters, which are something we hadn't previously had in Pint. That was a capability Pint didn't have. And it wasn't something we anticipated needing until we got fairly far into the process of making combined data sets and looked at this and realized, no, this isn't just one pulsar doing something strange. This is actually something that's common among many pulsars, something that's going to be an issue we actually have to address. And so one of the challenges of data combination is that as we make the combinations, we learn more about what we need to make combinations. So I've also put together, as we start to think about discussion, a list of some of the things that need to be done. There are basically, for this audience, there are 2 data combinations, both of which are going on right now. One is the IPTA third data release, where we're going to take the data from all of the different pulsar timing arrays, bring it together, and make a giant data set. The other is the combination of CHIME data into NANOGrav data, which I call CHIMOGrav. And those 2 things are at very different stages, and they're very different projects, but they also share a lot of the same basic scientific methods, and they also share a lot of the same personnel. So the first is the IPTA DR3. For that one, we need to finalize what data will be going into DR3. There have been times where we thought we were close to final in this, and then there seem to be, continue to be challenges. There's a bit of a game of chicken going on with the Meerkat second data release, who will commit to a timeline first. And we're also, see it again in the CHIMOGrav one, we're trying to get more CHIME data in here, and the LOFAR team have been trying to get their low frequency data in. They're about done with that. We also need to finalize some of our decision-making around FD jumps and DM jumps. That's a bit in the weeds, and I don't want to spend a lot of time talking about the FD jump issue specifically today. But that's an example of the kind of technical discussion we have to finish having and creating. There's still, I think, a lot of open questions on noise analysis and some on DM modeling. I think we have not spent enough time on noise analysis to feel confident that what we have is for sure going to work for DR3. There's also some discussion of whether we should be using advanced noise modeling for DR3, what that would look like, what the computational time would look like. So there's still several open questions here. And then there's the huge problem of the fact that we actually have to make combinations for 115 pulsars. That's a big task. Remember, the NANOGrav 15-year data set was 68 pulsars. There were a lot fewer ways for things to go wrong because we just had maximum of 2 telescopes with maximum of 2 receivers and, well, more than 2 receivers, but maximum of 2 backends. And so there's a lot of ways things could go wrong in the process of making these data combinations. One of the things we're trying to transition to within the data combination universe in the IPTA side is more of a projects over pulsars scheme. We have some specific project management terminology we've been using. But the key thing is I'm thinking of it as a transition from me or the other dataset leads telling you, please go work on pulsar 2145 minus 0750 to a scheme where sometimes we're saying, if you're a student or you're just lightly involved and you're just going to combine a few pulsars, we're telling you to do that. But if you're a more involved member of the team, instead of saying, go work on this pulsar and I'll make all of the mental decisions and all of the strategic calls, assigning people things like, hey, I want you to chair the effort to figure out the FD jump, DM jump thing. And then I will, and then report back to me and the other data set leads. We'll have a conversation and we'll move forward. So trying to move towards, trying to get into a scheme where we have more intellectual engagement, not just combination. And then we also have CHIMOGrav, and there's a lot to do for CHIMOGrav. This is a big project, and it's pretty under-personneled, I would say. It's getting better, but traditionally one of the challenges with Chime Pulsar has been that everyone who works on Chime Pulsar also works on something else, whether that be NANOGrav, Chime FRB, both. And so it's been a challenge for us to find the people power to work through these this huge stack of data, which we know is good data, which we know is really exciting and has a lot of scientific potential, but we haven't had a lot of time to work on it. So the first thing here is developing a proto pipeline. This is really in progress now. Mercedes Thompson at UBC has done a lot of really good work on this, as well as some other people. One of the things we're thinking about, with Chime data, because this is in the weeds, but because of it being a transit telescope, the beginning and end of the observation are not good for science. And so we're trying to figure out what the best and most advantageous way to cut off the edges are, whether that be using an existing model of the beam created by the cosmology team or purely cutting based on zenith angle. It's looking like the beam model is worth it. So we're probably moving in that direction. We also are dealing with things like how do we do RFI flagging? What kind of bad channel masks do we use? And just writing the Slurm scripts to run through a bunch of different stages of the pipeline. And our goal here is to create an initial 10 pulsar data set for DR3 that we're trying to do that right now so we can pass that off to the DR3 crowd. And then in the longer run, we're looking to develop a real serious efficient pipeline where we would press go and it would make TOAs rather than the more involved processing we have in the proto pipeline. And there's going to be about 50 pulsars from time going into the NANOGrav data set. So we'll need to make TOAs for all of them with this new pipeline. And then we will, once we've made those TOAs, then we can start the process we're going through with the IPTA DR3, which is actually combining the data into the NANOGrav data set. Now, knock wood, my experience has been that this is easier than we might expect because we were able to customize the TOAs so that they match the NANOGrav TOAs in a lot of ways. Actually getting them to appear on the same plot is not too bad. However, there's a lot of scientific questions that come with adding this additional high cadence, low frequency data set. In particular, we're likely to need to make some changes towards our DM modeling. And this is something that's going to need someone to really take it on and run with it and focus on what changes does it mean for DM modeling. And there's other scientific questions as well. And especially in the long run, these are things we're not even going to address for NGXX, but we'll eventually need to address. Polarization is a big, big question mark. Improved RFI removal. And we'd like to actually, use these new NANOGrav plus Chime TOAs to do really interesting science. There's some evidence that this will be really nice for binary modeling and for other sort of pulsar science applications that we're really excited about. And we do want to take the time to do. So one thing that's important to talk about is timeline. So for DR3, we are aiming for a late 2024, early 2025 completed data set that we can pass off to the GWA. We have some early data sets in progress now that are basically providing an opportunity for the GWA to do methods development. And maybe there'll be some science out of that, but most likely it's just methods development. That's our focus. Right now, we are working on the proto pipeline and the first 10 pulsars or so for ChimeGrav so that those can go into the IPTA DR3. It's important for a whole bunch of reasons that Chime be represented in that data set. And it will also provide us a nice training ground for the NGXX version of ChimeGrav. Now, the challenge here is we're aiming for late 2024 or early 2025 with NGXX. And I want to draw your attention to the fact that the timeline for DR3 and this preliminary NGXX are basically identical. And for the data combination team specifically, this could be very challenging. So this is going to be a lot of the same people working through these two very large, very scientifically intense projects at the same time. And so that's going to be a genuine challenge for the data combination team in the coming year. So why is the Wallaby so worried? And after this, we'll get on to the conversation. But this is my signature data combination Wallaby. He's worried. He's always worried. But right now, he's a little worried that this is a lot of work to do on a very similar timescale. So one of the things I want to say to everyone is we're going to need people to be involved in data combination. And we're not just going to need people to be involved in data combination in the sense of like, well, point me to Pulsar and I'll do it. But also in the sense of I'm willing to, invest brain power. I'm willing to answer questions. Some of this may lead to additional science projects and papers. Some of this is going to be a little bit of letting our own egos go and sacrificing some of our time to something that is necessary to make the broader effort happen. And I know that's really hard, and I know that's really difficult, especially for people who are on the job market, who really need to be focused on first author papers and on things that will be clearly their achievements. So I think that's part of our challenge too, right? Is that this is really, really important, and it is science, but it is slow science. I don't want to call it service work because it isn't service work. It is, but it isn't. Like, it's work that serves the collaboration, but it is genuine and interesting science. However, it's genuine and interesting science that moves at a slower pace and that doesn't always end with a really clear, this is my first author paper. And so it can be a challenge to get involved in, but I also find it very, very rewarding. The Wallaby and I really want to see you all become more involved in data combination and want to build up a whole stable of excellent combiners, people who not just can run a notebook, but can also think through what it means to be combining something and help develop additional data combination skills as we start to look toward, as we try to get through this next really intense year to 18 months. And then also as we start to look forward to DR4 and whatever comes after NGXX. So that's my sort of intro pitch. I know from here we're meant to go into a time of discussion. I don't necessarily have a plan for how to facilitate that discussion. I'm a bit just throwing out, here is the data combination situation as I see it. And I'd love to hear what other people are thinking about in the context of data combination. If you have questions, if you have commentary, if you have, an idea for how to make the wallaby less worried, let me know.
There are not currently any questions in the chat.
So Sophia, I would say, I think one of the thing, like, yay, I'm excited you want to get involved. One of the challenges we have is that this isn't necessarily like sometimes we will have like a call for combiners in the short run where we're just saying like, hey, sign up to take a pulsar. And that's a great place to start to get a sense for what it's like to be a combiner, much in the same way that one of the ways we start people off with doing timing in the timing group is we say, well, we're gonna do a run through. Why don't you go ahead and we'll sign you up for a couple pulsars and learn the pipeline that way and sort of learn by doing. And I think that's a great way to start getting involved in data combination is to say, hey, I want to do a pulsar. One of the challenges we have right now with NANOGrav is because we're at such an early stage of the pipeline, there's a little bit more of a learning curve. So I'm working on building some resources that will be, we've had a conversation, it sounds like written resources are most useful. The goal is to have, as many people involved as we can, but right now it's still at a like somewhat high, somewhat intense level for you to learn how to do things. So I would say another thing you can get involved in, it's a great option is to attend either IPTA data combination working group or NANOGrav telecons, depending on which is more to your interests. NANOGrav in particular, I can say they're quick telecons. They're about a half hour every, 20 minutes, half an hour every 2 weeks. Currently Fridays at noon Mountain, which is 2 p.m. Eastern. And they're much more like small group, our team. The data combination ones are a little bit bigger. So I think we're working on making it easier for people to get involved. Yes, Rucker, I think that's a really important thing to point out. Rutgers been working on an intense data combination method. It's quite different than what we've done in the past. And it's, I think the consensus when we talked about it among the various dataset leads and co-chairs is that it's probably not what we want to go with for the main data combination for DR3, but it might be something we want to do for DR4. So Rutger, do you want to take a second and talk a bit about your method?
Yeah, that's fine. My take on a data combination is a little different than what is done with the IPTA data combination. So this actually goes back to one of the first things you said on, I think, the first slide, which is that whenever you add data, the data combination changes. So you have to rerun the entire pipeline. And my take on that is slightly different. I don't think of it in terms of the combination or the residuals, but I think of it in terms of the model itself. And yeah, the data combination changes if you change your data, but the model not necessarily need to change. Think about it like this. Think of the big data set we have now and the par file that represents the underlying physics. If you apply the par file we have right now to data we had for the NANOGrav 5-year data set, it's different. Would you be able to apply the current model to the 5-year data set? Absolutely. Even though it's a different combination. And the reason why is because the underlying model is actually the same, or at least compatible. So what I'm doing with my data combination, I don't think of it in terms of residuals. I don't even think of it as in terms of the complete model that includes all the what I call detector parameters. I think of it as a underlying model. Think of it as a likelihood function that represents the underlying physics. And that likelihood has, for every data set, a different set of parameters. But if you combine a data set, it doesn't matter from which set of parameters you start, the likelihood surface is the same if you combine the data sets. I don't care where the values are in the par file. I care about the likelihood surface. And what I've been able to show is that you can arrive at that likelihood surface if you do not rerun your pipelines. So I haven't been. I just merged the models in a way that I think is suitable, so that I can merge the astrophysics components of the underlying models, and those are models that can, for the underlying data sets, be represented with Pint or Tempo2, and I can combine them that way. So my take is completely different from doing an IPTA data combination. I want to not touch the data at all. I want to take the NANOGrav, the IPTA, the PPTA, the Meerkat, whatever data sets as they're being released, and I just assume that the PTAs have done a good job. And that is completely different from the IPTA data combination philosophy, where you want to recheck everything, make sure it's right. I'm not going to do that. I'm just going to assume that, at least to the 0th order, they have done their job well. Sorry, I kept forgetting FAST and NPTA. Of course, they're also part of the whole collaboration, and Chime and whatever. I just assume that those data releases have been done properly, and I'm just gonna take them for what they are, and I split up the detector specific parameters and the astrophysics parameters, and then I have a Pint model running underneath and a Tempo2 model running underneath. And because I do understand the astrophysics models and I make sure that they're consistent, I can just build up a combination like that. Of course, there are many questions on whether or not this is something that will give the same results as when you do an IPTA data combination. But that's the approach I'm taking. I would like to not do IPTA data combinations anymore in the future. I'm not there yet. I can say we have a rudimentary data combination, still ironing out a couple of kinks. I'm not sure, and I would love to hear from you what I should do with that combination, because I know I can't publish anything with it, but I would love to work with the community to get something out there. If possible, I've got a couple of students and postdocs. We could present something at the IPTA meeting where we'll have some initial results, I'm sure. I would love that, but I'm not even sure what I'm allowed to do with it. I just wanted to mention that I've been working on this and it's becoming more mature.
Scott has his hand up and I want to go there in a second, but Rucker, I just want to say, I think the IPTA meeting would be an excellent venue to present this at. I think one of the challenges of this session is that I don't want to spend too much time talking about what we might regard as long-term development. I think it's a really interesting idea. I think we're all really excited about it as to see where it goes. But I think the consensus right now is that it's not what we want to do for DR3. And so I want to, and we can't do it for NANOGrav because it's a very different combination question. And so I think I want to be careful we don't spend too much time talking about this, but I do want to go to Scott.
I was actually going to say something almost exactly opposite to what you said, because I agree with a lot of what Rucker has said. I think the reason things are very hard now, and they are, I 100% agree with everything you said, Deborah. The reason things are hard now is the way that we do things, as well as what was mentioned in the chat by Ingrid, which is the really crucial thing. And there was the assumption that Rucker said that the PTAs are doing the right thing. Well, we're not, because every PTA is doing something slightly different. And the greatest example is the wideband, how we treat wideband data, because since pulse profiles change with frequency, and there's also frequency dependent astrophysics, the ISM and the scattering and stuff, and that causes all sorts of crazy covariances that each PTA does differently. And you even showed that in your talk, Deborah, about the the GMRT data having problems with that. That's the type of thing that we could solve in a method that Rutger's talking about if the models can account for that. Right now, I think that the models, we do not have any models that can do that well, but this actually could be a much faster, much better way of combining all our data, even for DR3 or CHIMOGrav, if we were able to pursue this type of thing. So while I agree that it's a long-term type development potentially, it could save us huge amounts of heartache, even in the short term, if Rucker and maybe others were willing to push this. I mean, there's a possible parallel development stream here that really could kind of revolutionize the way that we do data combinations, because this is only going to get harder in the future. I mean, we're becoming more international. We're using more telescopes. We're using wider bands, more pulsars. I mean, this problem is only getting worse. figuring out good ways to do this, including for our current data set mergers, I think is worth looking at in detail now.
I agree. We should definitely pursue it in parallel.
Yeah, agreed. One thing you were saying, Scott, about the telescopes doing things differently. I have been thinking about that a lot, especially those FD jump and FD parameters and stuff like that. I keep those separate. So in a way, that whole discussion that was going on, especially in the fall, where we had to implement different FD parameters per in order to make them compatible, I didn't have that problem because I kept those separate for every data combination. I also appreciate that that's not the entire story, so I'm not going to pretend it is. But there's definitely a bunch of stuff that can be simpler by keeping things separate.
I'm just wondering if, so I think there was a DR2 Lite. I'm just wondering if there are lessons from that that could be applied to this, when the idea of taking, in that case, you know, it was just picking the best timed pulsar from a given PTA, and using that, how am I saying this? Like, say multiple PTAs times 1713, of course, but we only pick the best timed pulsar from whichever PTA times it best. I'm just wondering if that would be somewhat analogous to this. At least maybe there's some lessons to take from that. I don't know. I'm just kind of posing the question. If anyone knows.
Megan, that's a good question, but I'm not sure anyone who did DR3 or DR2 Lite is on the call.
Yeah, no worries.
I'm not sure it ever actually got completely finished.
Right.
Ingrid, go ahead.
Yeah, I was just going to go ask Rutger. I mean, you're saying you keep the, oh, my video's not starting. There we go. You keep the FD parameters separate. I don't think I quite understand how you do that and why it becomes not a problem. I know, Deborah, you don't want to spend too much time on Rutger's method, but I'm just, it's intriguing enough that I think I'd like a little more clarity on that. Thanks.
I spend 1 minute on it, suppose. So the FD parameters, they're in the individual PTA datasets. They're defined by the PTA separately as a way to account for the frequency-dependent pulse profile evolution, and that is either in Pint or in Tempo 2 for that one dataset. I just make sure that those parameters are only fit for that data set, and the ones that have been defined for another PTA will only apply to that data set, and I keep them separate.
Oh, I see. Okay, it's that
essentially how it
simple.
works.
Okay. I think long term we want to aim for something more global, but anyway, I'll let other people have their thing to say.
Thankful, go ahead.
Yeah, hey, so Rutger, I've already talked to you a lot about this new method, and I'm really excited about it. So I think that's really exciting, and I'm excited to see some preliminary results. I do want to bring up, though, I'm going to be annoying and say that I want to make sure that the sort of power of the IPTA combined data set as a, you know, sort of secondary science helper is really, really important, right? We can get a lot of really interesting science out of the solutions that we come up with from the combined data set. And with this method, it's not immediately obvious that we would be able to sort of get what the pulsar timing community expects in, you know, PAR and TIM files. We'd have to do some adaptation to really get the most out of these results. And so I just don't want secondary science to get lost in this conversation, because it really is super important for the pulsar timing and pulsar science side of things. But I do genuinely believe in what I wrote in the chat. I think this is an awesome opportunity for sort of simultaneous work.
I'm going to take Chair's prerogative for a second to say, yeah, I think Thankful makes a really important point that although yes, in the context of pulsar timing arrays, our primary science is searching for gravitational waves, our secondary science is also really important. And a lot of people have built, you know, whole careers on the pulsar timing data and the things that we get out of the sort of secondary science. And so I think we want to be careful that we don't make things so efficient in creating the gravitational wave solutions that we then lose the entire ability to use that for other science applications. So I think I've said this, but I think we definitely want to pursue more of Rutgers' method. I think it's potentially really interesting. I don't know that I'm not sure all bugs are ironed out. And I think, even if all bugs are ironed out on a DR3 timescale, I think what we're going to be looking at is a parallel result rather than instead of, just based on conversations I've had with the other dataset leads. I think the general air is this is really interesting, but we want to make sure we can compare a final result from each method. Ken, go ahead.
I have a question about something else, which is the scheduling of NGXX and DR3. So DR3, we have this early DR3 that we can look at. The idea is to have some sort of final version of DR3 ready to analyze in a year or so. Is the NGXX going to go through some similar pathway starting a year from now? Or are we going to have like the whole DR3 and the whole final NGXX thing and trying to analyze them both at the same time?
The dataset leads, so thankful Michael, Megan might want to weigh in a little more. My understanding is that the dataset at the end of 2024, beginning of 2025, will not be the final dataset, but will be a full dataset. That there will still be that it will be a full-scale dataset intended to be used to create a preliminary gravitational wave result, but that it will be likely to go through additional refinements. So yes, I think I see the same bottleneck you're potentially seeing, where it becomes, we have so much to data combine now, and then in a year we have so much to gravitational wave analyze. It could be challenging. Thankful, go ahead.
Yeah, I just wanted to second what you said, Deborah. I mean, I think that there is a very obvious point where there needs to be simultaneous development, and that is for NANOGrav, right? Because that's going to affect IPTA and the next NANOGrav data set on similar timelines. But I just wanted to clarify, we are going to have a session about this on Wednesday afternoon. And also, this first data set that we're sort of aiming to have published before the PFC2 deadline and everything is not, as Deborah said, going to be a sort of full combination, but it is going to be something where we can build off of it. But there's going to be a lot of conversation about this on Wednesday for sure.
Zaven has graciously given us a couple extra minutes, but we do need to wrap up relatively soon. So are there other things that we want to discuss or need to discuss? Great, then it sounds like we may be able to actually get done closer to on time and move on to our next topic.
Hi, everyone. I just got the thumbs up from Zaven that we can get things going. So I'm kind of a stand-in moderator for this session, kind of at the last minute, i.e. yesterday, to handle a little bit of discussion about how we do pulsar noise modeling. So this is kind of in discussions between basically the noise budget working group and the timing working group, but also obviously that heavily impacts how the detection working group does their things with our data sets as well. So I have this one slide just to kind of set the tone, and I think we should discuss. I'd love to hear people's opinions. It would really be great if like Jeff Hasboon was here, but I don't think Jeff is here.
I'm here.
Yeah. Oh, you're here. Excellent. Good. I expect you to be jumping in all the time on this.
Okay. I'm also putting in my final grades at the same time. So.
Okay. Fantastic. All right. So just to, especially for the students, just so they would have a one sentence understanding of what we do for our noise modeling right now, is that we do our timing, our technical timing solutions that have been done with pulsar timing for 50 some years. That's done with Pint currently, but could also be done with Tempo or Tempo 2. But then we model the noise through the Bayesian model selection process, both in terms of white noise, which are our EFACs, E-quads, and E-cores, plus, if needed, any red noise parameters. That's done with Enterprise. And the way this happens right now is we do not do those simultaneously. It's an iterative procedure where we get Pint, we then run the noise analysis with Enterprise to get first generations of those parameters, rerun the timing with that first generation of parameters, and effectively do that a couple times so everything converges. And that does work, but it demands a lot of person time and feedback, and we have to check to make sure if things are changing. This is why our development for the last data set involved, a lot of timing code that tried to do this as automated as possible, looking to see if timing model parameters needed to be added or removed after the last additions of noise. So that's the way we do things now. So just a handful of things we could talk about. Can we better automate this procedure? Can we do it simultaneously without that iteration? And I think this is a little bit about what the nonlinear timing projects that have been going on in NANOGrav is kind of pushing for. I think enterprise could even potentially do it now, I think. Can we do it, i.e. what I just said, but is it even computationally feasible? Would we even want to do it that way? And then the stuff that like Jeff and others have been leading up, what about noise modeling and advanced noise modeling? Every pulsar is a special flower. And, some pulsars are really special flowers, i.e. really stinky ones like 1713 that need a lot of special attention. And if we have to do this on a pulsar by pulsar basis, how do we handle those zillions of potentially different permutations that we have to check and all the person power requirements to do that all correctly? And do we need to do that? Do we need to do that on only a couple pulsars? How do we decide which pulsars to do that on? And then finally, how does this interface with our ongoing and slowly converging pursuit of doing true wideband timing in the future? Are these things compatible in any way? Do they diverge? Does the need of, to doing, correct advanced noise modeling to handle frequency dependent things in a much better way? Can we not do that with some form of future wideband? These are the types of things I think we can spend whatever it is the next 25 minutes or so discussing. So I will leave it right there, and hopefully we have just some comments, and I would love to hear from people. Jeff.
Thanks, Scott. I have thoughts on a lot of these points, as you expected. I actually want to talk about the nonlinear timing piece. So, Andrew Kaiser worked on this quite a bit before he left the field, and we, Maura and I were working on this with him as well. And a big part of this was trying exactly to do this idea of running the normal timing with the noise modeling at the same time. And so I think for the vanilla noise modeling, this is completely possible. It is a little bit slower for sure, but not as slow as you might think. So for instance, for the really slow pulsars like 1713, the time is still really dominated by the inversion of the covariance matrix. So the fact that there's so many different white noise parameters and so many TOAs in 1713 is still the bigger bottleneck than going through all of the timing parameters as well. And so it is possible, and I think we could do it. It would just take a little bit more development. It's sort of almost there, right? The paper's done. There's a branch of enterprise extensions that has all of this stuff in it. I know that Rutger is thinking about doing this in a much faster way as well. And some of the recent talks we had about accelerating the code via either using JAX or GPUs could probably really help us with this as well. And so it's one of those things that with like 3 months of development and a few people working on it, it could definitely get done. I kind of feel that way for a number of the things on here. So it's, I think it's the thing about it, I guess, is that it's right now, it's probably, I don't know, 50% slower than running a regular noise model, or maybe 70% slower. But if it means that you don't have to iterate, then you gain speed ups there. So I don't know, it might need to be tested to really see if what I'm saying is true or not. But anyways, that's the first point I wanted to make. So it sounds like David has another point.
David, you want to talk about this part specifically?
Yeah, a little bit. First off, thanks very much. Scott was put in this position at the very last moment. I think this is a really excellent list of talking points here. And since Joe Swigum was doing the last data set, and I spent an awful lot of time talking to him about it, I recognize that this jumping back and forth between noise modeling and timing really was a huge barrier to getting things done in a timely manner. And Jeff was talking about, I think there's two aspects of it, and Jeff was talking about the CPU time aspect of it, which I think is important. But I think a separate thing is just jumping between Pint, then Enterprise, then Pint, and that sort of weird iterative loop, if there was a way of getting rid of that, of combining everything so that enterprise acted as a sort of like fitting routine for pint or something like that. I don't know if that's appropriate language. I think that would be the dream scenario, where even if it's going to take a couple hours to run or even longer, if you just type that and go home and wake up the next morning and it's done, as opposed to you have to run something in Pint and then send it off to WVU and it runs on Enterprise and then it gets sent back to you and you run a big script somewhere else. That iterative process, I think, also really slows down our process. And it's really disheartening for the people who are doing things. So I don't know how feasible it is to get everything integrated into a really it works package. And I'll say, I think at the end of the day, Joe really did actually have like a script that would do all these things, but it still felt at the end of the day like an iterative process. So I'm interested to hear people's reactions to this.
Yeah, Jeff's hands up next, and then Lulu.
Yeah, just to add on to what David was saying, I do think there still has to be iteration because the timing model is going to change. So in the Bayesian sense, right, you can include extra timing parameters that you think might be there and basically do the same thing that we do with red noise. So if the Bayes factor is low enough, we just don't include that timing model parameter. It would be a different way of picking what timing model parameters are in there. And that's I think a big part of what would have to change here. If you wanted to decrease the number of iterations, you might end up in the end wanting to run it with the sort of bespoke timing model that you have in the end. So that's a part where I'm definitely not an expert, and we're not doing, the various statistics that are used. I don't know how to incorporate that, those statistics that are used to choose which timing model parameters are included or whatnot. So I still think there need to be iterations. I just hopefully it would have to be fewer of them.
Yeah, and do you mind if I interject?
Yeah, and I'm going to use prerogative too to directly respond as well. But go ahead, David.
Yeah, so I think that's a good point. I would say, and I imagine that Scott's going to say the same thing, for 95%, 98% even of our timing solutions, we actually know from prior experience what the relevant timing parameters are. There are arcane cases of binary systems and things like that, where we're not quite sure exactly what the best model is. And then the next data set, we figured that out in the 15 years or so in the XX data set, it should be fine. So I think we probably are inefficient that way. We probably reinvent the wheel in terms of model selection far too much. And maybe it makes sense to do that once for each pulsar at the beginning of analyzing a new data set. But after that, we should just ride with it, ride with what we have, I think. And I think that includes FD parameters. Sure, why not? Just be fit for a couple and at the end of the day, that's what we're doing, like with the wideband. Fit for a couple FD parameters if you're not sure, and just move on with life, because that shouldn't hurt anything. And if it is hurting things, then there's something bigger that you need to worry about. So maybe that's a procedural thing where we need to think more clearly about what's important and what isn't important. So
yeah,
sorry.
Thanks, David. I'm going to do my quick interjection, then we'll grab Lulu. And maybe mine is kind of similar to what Bensei mentioned in the chats as well. But one thing I was wondering, if we're doing some things in a full Bayesian methodology, why not always include all timing parameters, in the analysis, and let the data just decide, how to weight each one based on what's in the data? Does that actually kill us in some way? I mean, we're looking for really long period or long, for at least gravitational waves. We're looking for really low frequency things. Does it suck out any gravitational wave signal for us? And I'll let people answer that. Lulu.
Okay, my question is somewhat unrelated, but one thing that I've heard many people say is that advanced noise modeling is to some extent incompatible with wideband timing, but I've never heard any detail about what makes it incompatible and what might need to change to make it compatible. So just like somebody who knows more about this to speak a little bit on it.
Jeff, do you want to give a 1-minute summary, and I will hold you to 1 minute?
Yeah, it's pretty easy. When you do the wideband timing, you fit a DM data point. So you fit out DM at a given epoch, and then you have that DM. The problem is that there's two problems with that, is that if there's actually scattering in the pulsar, you don't have that information anymore, because you've sort of fit out all of there's no more frequency dependent information, because you only have one data point per band per epoch. And then the other piece that's even more subtle than that is that when you fit DM daily, like you do in DMX, it actually is fitting out a little bit of scattering as well, because you're not imposing that things are changing together over time spans. So DMX also fits out a little bit of scattering. It can fit out that 1 over frequency of the 4th or whatever it is as well. So you're pulling out some of that signal too. So we just don't have you no longer have the frequency dependent information in order to do the modeling of the higher order frequency dependent processes.
Great. That was excellent. Thank you very much. And Lulu, does that answer your question?
Yes, thank you.
Awesome. Joe and then Maura.
So I wanted to just chime in as the person who pressed the button quite a few times for the 15-year. We do definitely have a lot of methodology in place to make this process a lot more streamlined. We do need some more work to be done on it. And I think that is greatly, at least on my end, I can provide a lot more help now, so I have a better understanding of how the whole process actually goes after we finished up the 15-year. But that said, I think trying to integrate the two software packages a bit better in terms of like how this iterative process is actually going to be piped in from one to the other. I think that's kind of a lot more critical. I've lost my train of thought slightly, so I apologize there. There's been a lot of really good points, and I've been jumping around in my brain. So
great. Well, thanks, Joe. Maura, and then Ross.
Yeah. One quick comment just related to what Joe said. I hope that when we streamline this process, anyone should be able to run our noise modeling. I think one thing that slowed us down a lot was the fact that we only have like very few people who can actually press the button at WVU. And I know that's sort of this historical issue, but I think that's another reason it's been slow. It's not just the wall clock time, but like just the actual small number of people that can do these kinds of analyses. But that wasn't my initial comment. My initial comment was related to Scott's comment of just like, why not just fit for everything? And I think, with the work that Andrew did, well, one thing is it's just gets to be a mess because there's lots of covariances and things that are found to be moderately significant. And then also some things that are just astrophysical. So one thing I wanted to bring up is that I really like the idea of like including there's some astrophysical priors, like things that we already know. Right. So like, obviously we shouldn't fit, this is an obvious one, but like fit binary parameters for pulsars that we know are not in binaries. In Andrew's work, he also found a couple other interesting things. Like there were some pulsars, like 1600 minus 3053, I think, which like the mass always ended up being fit to be like greater than 3 solar masses. Right. And so there was something else, obviously, which was getting absorbed into that Shapiro delay fit and then restricting the prior, so it was forced to be like less than 3 solar masses, for instance. Both shortened the time needed to find a timing solution because it restricted it to a narrower range and just made it more physical, right? Similarly with like constraints on parallaxes or proper motion, say from like Gaia measurements of companions or something. So I think this would be a cool way to just narrow the range that we're searching over things. I also know in Andrew's work, it did take a long time to do the nonlinear timing, but he was also searching like a huge prior space, right? Like starting at the values from the initial timing model and searching like minus 50 sigma to plus 50 sigma or something like that. So I would take comments about it taking a really long time with a little bit of a grain of salt, because I don't think we came at it. I mean, Jeff maybe disagree, but we didn't come at it with like an efficiency lens, right? It was just kind of like, see how this works. But I think it could be done much, much more efficiently than the way that we did it. And I think as we get timing for longer and longer, right, like we're going to expect things to deviate less and less and less. So we can start with much narrower prior ranges as time goes on, and I think move to much greater efficiency and be able to hopefully fit for like everything all at once in a way that's way faster than what we're doing now. And by the way, just like a little mini advertisement, I just sent Andrew comments this past weekend on this paper, which we need to get submitted. And if anyone is listening and is interested in this, he's going to send it out very soon for a final read before submitting it. So stay tuned.
Great. Thanks, Maura, for all of the comments and for that news. Ross.
Yeah, so just in response to what Jeff said earlier about the incompatibility between wideband timing and the advanced noise modeling, I want to point out that in principle, there's a path forward that we could try there, which is that even though in wideband timing, we're kind of getting rid of some of that information about the frequency dependence by fitting only for a single TOA and a single DM across the band, we could include other things in that step of fitting for the TOA and DM. Like we could simultaneously fit for the amount of scattering that affects this particular observation. And that's something that we would have to do a lot of development work on in order to make it work. But in principle, is a way that wideband timing could be made to work with things like advanced noise modeling.
Great, thanks for that, Ross. Yeah, and I would love to see that type of thing. If nothing else, just to make our data sets smaller, especially as we move into the wideband, the really wideband timescales. Jeff?
Yeah, I think so. David Kaplan asked made a similar comment in the chat, Ross, and I think you're right. I think there are paths forward. The issue is that we don't know. So when we do model selection, when we free up the index of the radio frequency dependence of the next order term, whatever it is, we have the DM is 1 over radio frequency squared, and then something else that's probably near 1 over radio frequency to the 4th, but that's really only true if the ISM is absolutely uniform. If it's turbulent, it's supposed to be to the 4.4. In a lot of pulsars, it's to the 3.6. And so the preferred index is different. And then besides the scattering, something like 1713's dips, the preferred index is 1 over radio frequency to the 1.13 or something like that from the probably profile changes. So what we do and what we fit for in the wideband kind of locks us into something. And so then we'd end up, I imagine we'd be doing a lot of iterating, which doesn't seem like something we want to do. I would love to brainstorm ideas if there's some way of fitting for generic frequency dependence in the wideband TOAs, like if there was a way of getting some kind of PCA of frequency dependence, something like, Ross, in the plot you have of the dips for 1713, there's this great plot of how the TOAs, what the index is basically, or yeah, I think it's what the index is, or maybe what the delay is. It's obvious that delay is different, has different dependencies on radio frequency at different frequencies. I don't know, something like that. That's just spitballing, but it might be worth everybody thinking about that. If there's some other more smooth kind of function we could implement in wideband.
Scott, you're muted.
Thanks, Dan. Yeah, I was talking. So I was looking to see what time this session went to, and it looks like it goes till 1/4 after or 20 after. I'm not quite sure. So we do have a little bit more time.
Go to 3:20.
Yeah, okay, great. So some specific questions about our next data combinations, including NANOGrav and truthfully, even our next NGXX data set. I think we will need to decide on my, and I did put my one slide in the Slack so people can see that if you want to go to the Slack, about how much advanced noise modeling should we put in. We know 1713 has serious issues right now. We want that pulsar in the next data set. We are going to have to do something special with 1713. But how many special flowers do we want to include? And how much time and effort do we want to put towards that? That is something we're really going to have to think carefully about. There's also been several high HDM pulsars, several of the 16 pulsars, that start with 16 are disasters. 1903 has tons of scattering and dispersion. It's potentially a disaster. And does anyone have thoughts on these? David.
Yeah, so this is not a very well-informed thought, but with something like 1713, which has had a couple, really disastrous periods of timing, a conservative and effort-saving thing would be just chop out like a year's worth of data or something like that, which sounds pretty horrible to do, but compared to making a bespoke model for that period of time, it really gets you the same result at the end of the day. Your bespoke model is going to have enough free parameters, either literally parameters in the model or different options you've thought about and used or rejected, that it's equivalent to sucking all the power for detecting gravitational waves out of that data. And I think in practice, we ought to be pretty, I don't know, liberal, I don't know if it's liberal or conservative, but pretty aggressive about just chopping out sections of data from individual pulsars that are misbehaving rather than spending lots and lots of times for the purposes of gravitational wave detection on those data sets. I mean, very interesting to look at. So papers like what Ross has worked on and that kind of thing, very much in favor of that. But that's different, I think, than the gravitational wave analysis. And I think we should be willing to throw out data, things like that. I'm now going to contradict myself and say, but then the thing that keeps me up at night is, what if those 1713 events are also happening at a lower level in 1713 or in other pulsars that we have? And I guess we take the approach that, well, if we can't see them, then we might as well assume that they're not there. But that's something that makes me very nervous when I say start throwing out bad data.
Yeah, I totally agree, David. And just to, for 1713 is a great example where I think we could shove out maybe a year of data, but like the bad boy 16s, 1643 and 16 whatever is the other one that 1642. Anyway, there's a couple of them that have 16s that have crazy like frequency dependent ISM related junk. That's all the data. Like, do we just throw those pulsars out, or do we have to somehow, treat all them separately as well? So there are a lot of different things going on in our data set. Steve.
Yeah, I'm going to ask a question I feel like I should know the answer to, but have we ever done a study of like simulating crappy data and then just measuring how our vanilla techniques respond to that? So all of these problem pulsars, all of the higher order chromatic effects we're worried about, have we just tried not leaning fully into doing every single pulsar like that with advanced noise models and seeing how our standard techniques respond? Because that could lead the way in making a decision tree of what are the important effects, how does it affect lower frequency signals, correlated signals, et cetera,
Yeah, thanks, Steve. And that might be related to one of the other comments that came out in the chat by Jeremy, which is that the results from the 15-year custom noise project could help inform that. And is there a summary on what's the status of that? It'd be great if someone would let us know that. Maura?
Well, I wasn't going to do that. So if someone wants to do that, they should jump in.
Well, yeah, go ahead first, and then if someone's willing to give an update, they can do that.
I mean, I was going to advertise work that Jeff put a lot of effort into this, and my former student Brent Shapiro-Albert wrote a paper using the pulsar signal simulator. And so this is a Python package, and the goal was to kind of do exactly this, like to put in both kind of like deterministic astrophysical effects, but also sources of noise, RFI, scattering, whatever, push the data through our like real timing pipeline and then see what's recovered on the other end. And I think we should really get back to using that package. I think there's a lot of other things, and Jeff, you might want to pop in after I'm done talking about this. Maybe you disagree, but I think there's a lot of functionality that could be added to it that would really help us. For instance, like putting in pulsars like 1713 and pushing them through the timing pipeline and just seeing like, how do we recover pulse shape changes in a way independent of other timing parameters. Brent did a little bit of this where he measured dispersion measures and then saw how scattering delays would get absorbed into those DMs, like how much the DMs were affected by scattering, like how much of that got absorbed. But there's so much more that could be done with that to answer some of these questions, like along what Steve suggests. great student project if anyone is interested, I think. Jeff, yeah, I'll pass it over
Yeah,
to
I
you.
think, yeah, Maura, I completely agree. I mean, an end-to-end types, fully simulating, well, some people don't even know this. The original idea of PINT was to fully simulate pulsars literally from the pulsar reference frame, the electromagnetic emission, clear to the back end post timing. That was one of the original projects, and we got rid of all the simulation bit. But yeah, I totally agree. Simulating as much of that stuff and then seeing how we can measure it or remove it is a great idea, and we should push that forward. Jeff.
Yeah, I can give an update on the advanced noise modeling too, but I'll talk about the PSS. So I think yes, the core of what needs to be in there for the signal simulator is there, and Brent made everything work, but a lot of the connection to actually getting everything out was written in notebooks that only really Brent knows how to use. And it does need a little bit more, let's see, there's lots of projects to be done there. I think for me, I was sort of assigned to that project early in my PTA career, and it's definitely out of like the basal pulsar stuff and how the telescopes work is really out of my wheelhouse. So I'd be very excited about collaborating with like another senior person who had students who were interested in that, for sure, like Maura and I did. So if people are interested in that, definitely, but it's not something I feel like I can lead a lot of those because yeah, good, thanks Maura, because of that. So I'll just put that out there, but it is all there, and I think the framework is really good, and to build it up. And there have been a lot of people interested in the code, ask me questions about it sometimes. The advanced noise modeling is moving along really well. So Jeremy and Bjorn are leading this work. We are almost at a stage where we're going to get final bespoke models for the pulsars. Getting the model selection, we've really honed in on getting the model selection down pat and how to figure that out. And so I imagine by the fall meeting we'll have a pretty good update about that for folks and have models in hand, and hopefully have run some gravitational wave background runs even by then. So I think this summer we're pretty much going to get all of the bespoke models done. So maybe I'm being optimistic. But.
And quick question about that, like you said all the bespoke models. Does that mean every pulsar gets a bespoke model, or is there a subset that get that?
We've done it for all of them, and we probably will in fact, we've even taken away the DM model for some of the pulsars. So not even DMX, just because there are some pulsars that when you just use a solar wind model, that's all it seems to need, and a DM1 and DM2. So at some point we probably would come and ask the timers whether we need it for all of the pulsars or not. And that's part of this process, is we're actually keeping tabs on how long things take. So for some of the pulsars where, you might have a base factor of like 5 in favor of something, but if the other model is 10 times faster, then we might just choose that model because of that. So it's something we're definitely keeping in mind and keeping track of. And at some point we're going to ask the collaboration what the best ideas are for that.
Great. Thank you very much for that update, Jeff. That's really interesting. Steve.
So I think the answer to my question earlier is no, right? We don't fully understand how some of these misspecified noise processes might be affecting our gravitational wave inference in our pipeline. So that's good. I haven't forgotten something really obvious, but it does seem really important that we use that to simulate and generate kind of a decision tree of importance for tackling these things. There are a couple of papers that I remembered in between that have looked at this, like Katerina Tabertsi's paper on different things that create spatial correlations. And then Ryan Shannon looking at how secular profile changes creates red noise. And then I highlighted Valentina DeMarco's paper that came out maybe last week that's looking at some things. I haven't read that yet, but it looks like it tackles some of these issues. But the literature seems pretty sparse, and it's something we should absolutely do.
Great, thanks, Steve. Ken?
I just wanted to add something about this question about if we put in too many parameters to model this, that, and the other thing, are we going to eat up the gravitational wave signal? So from a Bayesian point of view, this really is a question of priors. If you think that pulsars really have all these possibilities for all kinds of things that could be going wrong. And when you put them all in, then they can account for things without a gravitational wave background. Then you should be pretty worried, because that means that you don't know whether there's a gravitational wave background or not. And if you don't feel that way, probably it means that you don't really believe that pulsars have all these crazy kind of properties, in which case, regardless, you probably shouldn't put them in, because, we can't just put in everything. We have to use some kind of information about what we think is reasonable. Otherwise, it's impossible to be confident in anything. And I think we do have some ideas about what's reasonable, and we are confident in things, but we should think carefully about what we're doing.
Great. Thanks, Ken. Yeah, I agree. David?
Yeah, Ken, I think that's a really good question, but I think it's also important to understand that the vast majority of the parameters in our timing models have relatively short period implications or no time dependence at all, whereas the gravitational wave, the stuff that actually matters for our detecting and characterizing the gravitational wave signals, are things that vary on timescales of 1 to 15 or XX years. And so I think most of what we're talking about when we're talking about tweaking binary parameters or frequency dependence really are not highly covariant with the gravitational wave signal. So including them or excluding them doesn't suck out a lot of the gravitational wave signal. That starts to change when we do different ISM modeling for all dates and things like that. Then it starts to become important. So there are cases where we have to do it, but for a lot of these situations, it really doesn't affect it. But that's something to keep in mind. That's all I wanted to add.
Thanks, David. Dan?
Yeah, I was just going to say when David was saying most of the parameters have relatively short timescales, I'm glad he added at the end that much of the ISM propagation delay signal, both the part that we model and the part that we're not yet modeling, that has very long timescales, and that is probably quite covariant with the gravitational wave signal, which emphasizes why we should absolutely try to astrophysically model just as much as we can in our data, and only resort to more phenomenological models when we run out of physics that we can rely on.
Yeah, thanks, Dan. All right, well then the next thing, we'll cut this right now. So there is a lot of stuff that we have to work on from this, based on this discussion over the next few years, that's for sure. And we will be doing that. So the next thing is a break, a short break. So we will start again at 3:30 for the next session, which is on, what is it on? Hot Topics 2, that's the ultra-wideband discussion. Oh wait, is it? No, I'm sorry, 3:40 it looks like. Is that right, Zaven?
Yes, 3:40.
3:40, so it's a 20 and a bit minute break. So talk to everyone again in 20 some minutes.
Thank you, Scott. Thanks, everybody.
Thanks for everyone for contributing.
Great. So next session is a 30-minute discussion on ultra-wideband issues and whatnot. There's a few different ways that I think this could go. I have a few slides just to update people on the status of the Green Bank ultra-wideband system, and a few slides that the timing working group provided, or that I made edited versions of. So just a few things to maybe set the stage, and then we can go from there. But if anybody wants to chime in with anything, please just go ahead. Okay. Just for people who I think this stuff has been tossed around a lot at this point, but just for anyone who's not like an observational radio astronomer and may not necessarily know what we mean in context by ultra wideband, our observing strategy, the GBT, historically had been to observe with two different receivers, two different front-end instruments on the telescope, from 720 to 920 megahertz and 1100 to about 1800 megahertz or so. Now with Chime, we still use this setup for a few pulsars, but for many others, we only use that upper range of 1100 to 1800 megahertz and get that lower range with Chime, or a portion of that. And this is important for accurate DM measurements, but having this dual band setup kind of lowers observing efficiency. And so there has been an increasing push at observatories around the world, as well as some successful developments that have come out of that, to use new ultra-wideband receivers, where ultra-wideband means that the ratio of your high frequency to your low frequency is kind of substantially more than a factor of 2, roughly. This is a good way to think of that. And that gives you better dispersion measure estimates, improves observing efficiency, also, in principle, at least can help to improve signal to noise. And so for a while now, Greenbank has been working towards a receiver that would cover instantaneously 0.7 to 4 gigahertz. So very similar in its operating frequency to the Park's ultra-wideband receiver. And so that's what we call Uber. So for those who don't know all the history here, the project has been delayed somewhat fairly substantially, and there's been a number of technical challenges that we have encountered. And the bottom line is that it's not as sensitive as we would like it to be, or that we need to be for it to, that it needs to be to offer a very clear benefit for NANOGrav to start using it and moving away from the way that we currently do things. Nevertheless, we are working to continue to improve it. So we are testing some new components that should be, or we are going to be going up on the telescope in mid-April. So we'll be able to test at least one of these new components. And that should help to improve the efficiency of the receiver in a relatively narrow range of about 2.5 to 3 gigahertz. But this is a range where we saw a lot of undesirable behavior in early tests. This is a kind of engineering drawing cross-section of the receiver. I'm honestly not entirely sure exactly what the colors all mean, but the yellow and black hashed parts here are these kind of ridges that sit inside the receiver. It has this kind of flared shape to it. The new component that we're going to be testing in April is a new design for those ridges that should help improve things. There is some additional things that our engineers are working on. This big part up here at the top, and maybe I should try and use the pointer, see if this works. Hopefully people can see the little box I drew around that. That part up there at the top is what I'm calling the aperture. We've gone through a few different designs for that, which hopefully will improve the amount of radiation we pick up from the ground, which is important for minimizing the amount of, or the minimizing the amount of noise, system noise that the receiver has. That will not be ready in April, but we're hoping that will be ready in fall. We're also going to be testing over the summer and installing for tests in the fall a new amplifier, which should improve the electronics noise above 3 gigahertz. But we are going to have to go through another round of testing in the fall. Unfortunately, testing won't be available in the summertime because there's going to be other work being done on the telescope over the summer, and there'll be long periods of shutdown. Sorry, now that my box is, my little yellow lines are not clearing, so I'll see if I can figure out how to clear those. Okay. Now I see some purple ones, but anyway. So just a few other updates. We're going to be going through kind of an internal retrospective analysis, and we are going to be reaching out to some other engineers and observatories for advice on ways we can continue to improve the receiver. And we are hoping that with the improvements that we have in mind, that the receiver will be a net NANOGrav or net benefit for NANOGrav to start using over the current observing strategy sometime later on this year or early next year. But we will need to reassess the performance and the benefits in the fall. But barring a major breakthrough, I'm not super optimistic that we're going to reach the original design goals on the receiver. There are still some sources of kind of excess noise that we haven't tracked down. It may be related to cryogenic components or possibly to other components of the receiver. So never say never, but that seems probably a bit optimistic at this stage. Nevertheless, we did do some test observations back in October where we were, so this was not with some of the improvements I just discussed. So we knew it was kind of suboptimal setup, but nevertheless, we did get some test observations. So we could get some actual on-sky data with all of the NANOGrav pulsars. as opposed to just a handful of pulsars that I was able to get data on during commissioning. That mostly went smoothly. We are investigating some unexpected frequency sweeps at the low end of the band. They almost look like it's not properly dispersed, and it's not in all pulsars. It goes in different directions for different pulsars, and it didn't show up in previous commissioning observations, even on some of these same pulsars. It's a little bit of a mystery, and that's something that we need to investigate in April as well. So I'll be getting some additional data there. This is something that Ross was just showing me when I was visiting Morgantown a few weeks ago. So kind of work in progress. But if everything works, and we do see these benefits that we're hoping to see with some of the additional engineering work, we are planning on switching to using the ultra-wideband receiver for observations that will be part of the upcoming proposal, which is currently under review, when it becomes beneficial for NANOGrav to do so. So that's an update on the ultra-wideband receiver. And I just have a few slides here that I got grabbed from the timing working group, just kind of talking about more narrowband versus wideband timing more broadly. So this is not necessarily specific to the green bank ultra-wideband receiver, although obviously it dovetails with that a lot. And again, just to make sure we're all on the same page, what we call narrowband timing uses one integrated pulse profile, idealized for each different receiver. And then profile evolution, changes in the emission of the pulsar are accounted for with these FD parameters. An alternative approach is to use wideband timing, which uses a frequency-dependent pulse portrait. So instead of kind of a 1D pulse profile, it's a 2D portrait of the pulsar as a function of frequency. So in principle, FD parameters shouldn't be needed, although in the 15-year data set, even when using wideband timing, there were about 10 MSPs that still needed FD parameters. So there's still some things going on there. And people, I believe Lulu, especially in the timing group, have been exploring RFI excision for the average portraits to make sure that they're not being corrupted in hybrid timing, like the IPTA, time-dependent scattering. So we can come back to this if anybody in the timing group wants to say more. There are a lot of benefits to using wideband timing. So although the raw telescope data with the ultra-wideband receiver is going to be greater in volume since we're covering a wider bandwidth, that data volume is not huge to begin with, but using wideband timing greatly reduces the data volume that gets input to the detection pipelines, which is the number of TOAs. So that has a significant benefit for detection pipelines. And then I just have a few other points here from the timing group. Eliminating the frequency information in TOAs will affect advanced noise modeling. Are they compatible? So maybe that's a point for discussion. And we think that the detection infrastructure can fully accommodate wideband TOAs. I don't know if there's anything that we'd want to discuss a little bit more there. And I think that is probably a fine place to maybe just stop and see if there's points of discussion that people would like to have, questions, or anything that I didn't mention that people would like to bring up in the next 20 minutes or so. And if anyone else from the timing group wants to chime in and say a little bit more about the slides that I had up there, please do so.
Yeah, I mean, just since, this is a pretty wide-reaching group, so I wonder if there are any questions about, I hope everyone feels pretty comfortable with the idea of wideband timing and how it differs from narrowband timing and all of those things, as well as like specific questions about timelines and effects on the observing program when the ultra-wideband receiver comes online, things like that. So, but I think you covered most everything, right?
Yeah, I see Scott has his hand up.
Yeah, thanks, Ryan. So I have a question for the collaboration as a whole. Let's say that in 6 months after we try these few new things that we're still not quite where we want to be, but we're pretty close. We're basically at very roughly nominally what we thought the kind of break-even line would be. Do we start observing with the ultra wideband if we're within, say, 5% of that line, even if we're on the bad 5% side of that line? This is something that this is not a hypothetical. This is even a potentially likely situation, because we right now do not know where this extra noise is coming from. Break even, yeah, we use the same amount of total telescope time, and our overall timing precision stays the same. That's what I mean by break even. Do we transition to this, or do we try to keep doing things now? Yeah, and Joris, I think I agree with what you said, which Joris says in the chat. I think it's better to have low frequency and high frequency data simultaneous. Yeah, I think even if the TOAs are the same, you know, basically that simultaneity removes a level of systematics from us. So even if we lose a tiny bit of signal to noise, that's a bit of systematics that we get back. The other thing that I think a lot of people don't think about, except for like Ryan and me and maybe Paul, is that having one receiver that NANOGrav uses, and probably most of the Pulsar community, really can help with scheduling, because, you know, we don't have to be switching around from 820 to a whole bunch of other prime focus receivers. If people are like most of the time using the ultra wideband receiver, that is a really big benefit. So like I personally think we should like make a commitment that almost no matter what happens come fall, we're going to start using the system. And it also, I think that also puts political pressure on Green Bank to make it work really well. But we all have to decide on that.
Yeah, can I just real quick clarify one thing? So the original plan for ultra wideband, part of the reason that it was going to be maybe a clearer win was that prior to the collapse of Arecibo and the incorporation of more of chime data, we were observing with that dual frequency setup for all pulsars. And part of the win for ultra wideband is that you wouldn't have to do that. So you are, instead of getting two 30-minute sessions at two different frequencies, you're getting, with the same total amount of telescope time, one 1-hour session covering that whole band. Because we no longer do that for many of the pulsars, that benefit is no longer necessarily totally applicable, but the plan would be for ultra wideband to not decrease the total amount of GBT time that we're getting. So the total amount of time for the project would still be the same. And I see lots of hands up, and I don't know the exact order, but I think Joe may have had his hand up first, so we'll go with him.
So just as one quick question here, because I do agree with Scott that I think it's pretty key that we switch to, you know, having a single receiver, just the very minimum, to make everyone's life at GBT a lot easier. Having now gone and seen what all has to be done to switch those receivers, it's quite a task. The question I have is, you know, if we made a switch, right, to just using the ultra wideband and it's not performing the way we were hoping it was going to perform, like currently, is it still performing at or, you know, better than what the receivers we currently have?
So this receiver, so it depends a little bit on the metric you're talking about. The system noise and in some parts of the band, the efficiency are not as good as the existing receivers. But when we've tried to kind of do a complete analysis using a lot of the framework that Tyler developed for analyzing which pulsars should be switched over after Arecibo collapsed and kind of predicting what the RMS residuals were going to be. Right now, for some pulsars, it might actually be a win. I think for most pulsars, we're below that break-even point. But on average, I'd say we're below it by a little bit. With the new improvements, I'm hoping that we get above that, but it's not going to be by the amount that we had originally thought about when we built this receiver. But some of that is also because the observing strategy has changed. David, you have your hand up.
Yeah, so I would entirely agree with what Scott said. I think even if we get a little bit of a sensitivity hit in whatever metric we're using, that for various practical reasons, especially having to do with getting all this data simultaneously, it is worth moving to the ultra wideband rather than waiting for years and dreaming that it will be the perfect receiver. We know that there are compromises that had to be made when we're going to a wideband, as opposed to that beautiful narrow band existing L-band receiver that Green Bank Telescope has. And we knew that this was a possibility. I do think it's important that we understand, and especially that GBO understands, that once we start using it, we really don't want them going in and tweaking the receiver anymore. It's critically important that we have an extremely stable observing system, that we aren't sort of adding in jumps or tweaks or whatever every couple months as some engineer really, really wants to change something. So I think it's very, very important to make that clear to the engineers, and that we understand that ourselves, that when we make a decision to switch over to it, unless something really, really drastically goes wrong or looks bad or looks different than we expected, that's a permanent change. So I just wanted to make that point.
Yeah, no, that is a good point. And once we get through some of the improvements that I just outlined here, there's nothing else that we know of right now that our engineers necessarily want to try, I think.
Yeah.
If that changes, then we'll kind of build that into the plan. But I agree that once we think it is good enough, barring something significant coming up that could really be a huge benefit, or something really wrong that we need to fix, then we should kind of freeze the design at that point.
Thanks.
Ken, you have your hand up.
Yeah, I wonder if somebody could explain about the connection between the ultra-wideband receiver and wideband timing, because it seems to me this ultra-wideband receiver receives the same information as our previous receivers, except over a wider range at once instead of needing to swap them. So if you want to do advanced noise modeling and you need some kind of frequency-dependent information, isn't that information there? Why do we give something up by using it?
Yeah, and actually, I think Paul may have just put something in the chat about this, which is that you don't have to use wideband timing to use the wideband receiver, but because the bandwidth is so large and the profile evolution is expected to be significant, especially for some pulsars, you may want to do narrowband timing slightly differently than the way we do it now. But you don't have to use the wideband timing 2D pulse portraitures with the wideband receiver necessarily. Scott, you have your hand up.
Uh-oh. Yeah, I couldn't unmute there for a second. Yeah, I basically agree with what David said. Except I think that, changing from one whole receiver to another whole receiver, which uses different, paths for the LO system and everything like that, is a dramatic, massive change that causes jumps and everything else. But like tweaking the ridges, for instance, or the outer, the outer baffles on the ultra wideband, or maybe even just switching out amplifiers, those will almost certainly do not cause big time timing changes, although we don't know that for sure, but they probably don't do that. So it is a little bit of a weird situation that it might be that if there's a potential big gain to the receiver, we might want to do that, and it might cause no timing change. But I do agree, pulsars in general, we want the most stable equipment as possible, but this might be a slightly different situation.
Yeah, David, you want to comment on that?
Yeah, I just think we have to be super duper careful because changing that hardware has the potential for affecting, for instance, the polarization response of the receiver, and that has the potential for affecting how we calibrate it. And even if in principle none of this matters and it all should be perfectly good, I would be very, very nervous about that. And I really don't want to get into the state where we're thinking, well, the fall and winter 2024, 2025 data are kind of wonky, so we end up throwing it out or something like that. Or nobody trusts that data from NANOGrav. I don't want to get in that situation either. That's all.
Yeah, just I guess one comment. I don't want this to turn into a discussion specifically about Green Bank, but I mean, I also will just say that I think that, again, unless there's a really clear win, I think that when we get to a point where we feel like this is as good as we can realistically do, given just realistic constraints, I don't necessarily know that there's going to be a lot of resources to develop to devote to little tiny tweaks and that kind of thing, just given other projects that are in the pipeline.
Yeah, can I directly address that, Ryan?
Sure.
And we haven't even talked about this because you weren't on the ultra wideband call that just happened a couple hours ago.
Yeah,
there's a chance that Moore Foundation wants to give us more money to make the ultra wideband better. It could even be an ultra wideband version 2.0. So you know, if with a bunch of extra work that's maybe even uses outside engineers and stuff like that, you know, we have to decide if that's something that we want to pursue or not. And we're going to need to discuss this and decide on it very, very quickly, because we might need to tell More Foundation that. There's a lot of stuff going on behind the scenes here.
Off the presses. So that's I mean, it's not a bad problem to have. I mean, it's not even a problem. So that's good to hear, and it is really good to hear that More is still interested in supporting NANOGrav more broadly and potentially this project specifically. But yeah, that does open up some interesting possibilities for down the road. So. So we have about 8 more minutes left. This discussion has focused heavily on the ultra-wideband receiver. That was probably because that's what I led with. But I do just want to see if there are any further questions about that or other topics that people would like to get into on wideband data sets more broadly. Okay, I'm not seeing any hands. So since we still have some time, I will just toss out some more things related to the ultra-wideband receiver. But please, if anybody wants to kind of steer the discussion in a different direction, feel free. You know, we made the point that this receiver is never going to be as sensitive, kind of the raw metrics of like system noise and efficiency as a narrower band receiver. But we have been we've been comparing the performance to the existing GBT receivers, and I think for this case we can limit the discussion to L-band. Our L-band receiver is actually pretty old, and it's not at all inconceivable that a redesigned and improved GBT L-band receiver is not going to have significantly better kind of aperture efficiency, but it's possible that we could shave a few Kelvin off of the system temperature. This is an idea that's been tossed around within Green Bank, but has never really gained a ton of traction. So I don't know that we need to go down that path too far, but just to say that if ultra-wideband seems like it's not going to be the win that we had hoped, and if additional funding from the More Foundation does not come through necessarily, it's an alternative approach to maybe think about, and one that may have support within Green Bank anyway. And and it's a lot lower risk because I think that the improvements are a lot more straightforward. So that's one thing. And if anybody does want to respond to that, please feel free. The only other thing I will say is that I appreciate people taking Green Bank operations into consideration when trying to make these decisions. And it is a realistic constraint that we have to work around. But I just want to make sure that everyone comes at this with the attitude of NANOGrav being an advocate for the things that are best for NANOGrav. And then Green Bank needs to kind of try and make that work as best as we can, given the other constraints. But everyone, I think, in Green Bank understands the importance of NANOGrav science, both broadly and to the observatory. And so we want to make this work. Ken, you have your hand up.
Yeah, so I know nothing about these things, but so this receiver, is it only going to be used by us? Do other users of Green Bank want to use it? What's the situation?
Yeah, so the driver here is NANOGrav. NANOGrav provided through the More Foundation funding for the project. And so that is the main driver, but there are certainly other people, many of whom are on this call and want to use it for things that are not necessarily specific to NANOGrav that want to use it. There's even some spectral line projects that want to use it because it covers a frequency range that the GBT doesn't currently operate at in the 3 to 4 gigahertz range. So it's a win for everyone if we can start to use this for NANOGrav more regularly and kind of switch to it as the main receiver, because right now it is difficult given the operational realities of Green Bank to just if NANOGrav is not using this, it limits its availability for other people. It's probably the simplest way to say that. But again, I think NANOGrav needs to be an advocate for what's best for NANOGrav, even though there are a lot of people in NANOGrav who want to use this receiver for other projects as well. So maybe it's a little bit difficult to sometimes wear those different hats. But as a collaboration, I think the focus needs to be on what's best for NANOGrav's core science. Thankful.
Yeah, I mean, I don't want to steer the conversation in a totally different direction, but I thought I'd mention at least that these issues with wideband timing that we've been having are one of the main sort of areas of methods development that are going to be necessary, or maybe not necessary, depending on how people feel, before the sort of next internal, the NGXX data set can be sort of created, right? And so I wanted to just re-emphasize, I guess, how much work has been done on this issue of FD parameters still being needed for wideband timing, and how much of a puzzle it really is. I know that Lulu and many other people have been working really hard on this problem, but I think that I think that this is a decision that has to be made both within the timing working group, in the sense that we have to see how sort of improvements on or effort towards solving this FD parameter mystery is going, but also I think it depends on the requirements of detection and noise budget and everyone else, right? And so I think that, it would certainly be helpful to hear the perspective of some detection folks in terms of reducing the computational load and how much of a bottleneck that actually is. I know I asked this at the fall meeting as well, but I just wanted to sort of get that back in the conversation. But I definitely don't want to take away from the sort of like talk about the actual ultra wideband receiver. But again, it is like a separate sort of issue.
No, I think it's fine to move away from the receiver specifically, although I think we are coming up against the end of the session here. But if anybody does want to respond to what Thankful said, we still have a couple minutes. All right, so I see Joe had his hand up, and then Megan after that. So Joe, go ahead.
So, and I know this is something that we in the folks in the timing group have been talking about a lot lately, but I guess the question I have for the folks that are doing, and I know we're going to talk about NGXX soon, but in terms of wideband timing, what would be the dream case in terms of like getting things going on fixing some of these things, like the FD parameters still being needed for some pulsars and stuff like that? Like, is it just, do we need more personnel? Do we need like that's kind of where I'm going with it. Like, what needs to be devoted to kind of trying to figure these things out?
Thankful, do you want to respond to that?
Yeah, sure. I mean, I will say, obviously we've talked about this at length. I think personnel really is a barrier. It's a job that will take more than one or two people, right? There are people with expertise in the collaboration who can do it. But I think that this is more of like maybe a programmatic conversation that I would want to avoid a little bit. But yeah, I mean, we need more people, right? I think that is very helpful.
Megan, you had your hand up, but I saw that Ross just raised his hand, so I just want to see, Ross, was that are you raising something, your hand in response to what Thankful just said?
I guess not really.
Okay, then why don't we go to Megan and then to Ross?
So, I mean, I think this is related to what Scott put in the chat, and I think Deborah mentioned earlier about there are like 4 or 5 different ways to do that people call wideband timing. I don't know. I mean, one obvious way that I can think of that I think at least some groups are doing is splitting your band and getting a wideband pulse portrait in each of those. But I was just curious if you could hear a little, excuse me, a little bit more about what other PTAs are doing, and if any of those would potentially make sense for us.
Lots of hands went up. Deborah, do you want to maybe respond to that first, then Thankful?
Yeah, I'll just jump in really quick. As Scott said, there is the description of what the PPTA is doing in their paper, and it is one of these variants as well. So one way to do it is to say I use a wider portion of a very wide band and make something that's more like a narrowband. The most common way people are using wideband timing is something along the lines of creating a frequency dependent template and then doing using it to make narrowband TOAs. There's also some rather complex stuff the NPTA is doing that's like a little bit different than that, that's supposedly allowing them to get away with Allegedly, that means they don't need FD parameters, and yet it does still require them to need FD jumps. So I'm not sure if it's exactly working the way that we thought it was. But the major ways are, you chunk up your band and you treat it as several receivers out of one ultra wideband, or you use the wideband timing to create a wideband template and then make narrowband TOAs using the wideband template, or you do full wideband. As far as I can tell, we are about the only people trying to do full wideband. Most of the other PTA, they're doing something more along the lines of a wideband template and then narrowband TOAs. And there are 2 or 3 other definitions just floating around. At one point, I did have a list of 5. I just don't remember all of them because some of them were pretty obscure.
Thankfully, did you want to say anything more to that? I think you lowered your hand.
No, all good. Yeah.
Ross, go ahead.
I was just gonna say about the wideband FD parameter issue. I know there have been a few people who've looked into it to some degree, but I'm not sure like what the results are that they've come up with. I can come up with a couple of different approaches that I think would be useful to look at. But I don't know if those have been done before. It would be interesting to hear from the people who have done some looking into it.
Just waiting to see if anybody would respond to that. But maybe that's a topic for future discussion.
I'll respond briefly in chat, but
okay. Ken, go ahead. You have your hand up.
Yeah, I was just going to try to say something in response to what Thankful said about what things look like from the view of detection. I can't speak for the detection group, but personally, extra TOAs at the same epoch don't do anything for me. From my point of view, it would be much simpler to have one. It speeds up processing a lot, and just makes the data easier to understand. It actually took me a while when I got into this to realize that there were multiple TOAs with times that were essentially the same. So I think the only question is, what do we lose by working with wideband data? If there's some fit that we should have wanted to do, and now the data are less accurate because we weren't able to do that fit at some stage of this process, then maybe we won't like it because our detection sensitivity is reduced. But it sure is convenient not to have the extra data.
Yeah, would anybody else like to respond to that? Okay, if anybody has thoughts, I guess go ahead and put them in the chat. Ross, you still have your hand up? Is that just leftover?
I mean, that is just leftover, but I guess I could say something in response to Ken. The one thing that we potentially could lose in wideband timing is some of the fits for frequency dependent effects. And this came up in the last discussion session with Jeff's conversation about the advanced noise modeling, because they can use the fact that there are many different TOAs at the same epoch to fit for frequency dependent effects like scattering.
Yeah, David, go ahead.
I'll also just make the other kind of obvious point that even in the ideal scenario where you take your full band, you boil it down to a single TOA, it's a single TOA and a DM. So there's 2 different things you suddenly have to account for in your data analysis. And if you add in scattering, then there's more free parameters as well. So it's not as simple as 1 number. It's at least 2 numbers in a very idealized situation. And if anything goes wrong with your idealized situation, then you need more numbers than that, which is, I think, why a lot of us like to hang on to at least a few numbers throughout the process. That's it.
Yeah, maybe I'll just say one thing to leave, and it's a little bit off topic, but it's somewhat related since you brought up the potential of scattering and the usefulness of having the wideband data for that. So it is not directly related to the ultra-wideband receiver project, but we are also developing a cyclic spectroscopy system for the GBT that can actually use the ultra-wideband receiver, but also other receivers at the telescope. And that actually is going well. And the benefits will definitely be pulsar and frequency dependent. But we hope that will be available for use starting in early 2025 is kind of what we're targeting, and I'm feeling actually pretty good about that. And Ross and Jacob have been doing a lot of great work with that as well. And other people on the call have been big contributors to the project. And that is something that we'll be able to use with the regular NANOGrav observing setup so that we can get those cyclic spectra and our traditional data products. So yeah, more data for everyone to analyze, but I'm hoping that that will help with measurement of scattering parameters and some other interesting things that we can do in the not too distant future. And yes, Ross did say he's presenting a poster on an update on that on Wednesday. So anyone who wants to learn more about where things stand there, that'd be a good thing to go to. Okay, we're within a minute of the updated end of the session. Any last minute thoughts that people would like to share? Well, then thank you for the discussion, and yeah, we'll have a lot more updates on this stuff over the coming next several months. So thank you, everyone.
Thanks, Ryan.
Okay, I wasn't sure whether I should start or we're waiting for a moderator, but I think we can just get going. Megan, looks like you're on. And Sophie is on. Okay, great. Yeah, so this is the IPTA discussion. Megan and I have put together a few slides just to kind of like kick off discussions. There's a few overview slides and then some slides with topics to talk about. Let me share my screen. Everyone see that?
Yep.
Okay.
Yeah, it's there, Maura.
Okay, great. It says now my screen sharing is paused, but can someone just tell me, can you see this first slide? Is it okay?
Yeah, this is Zoom with you sometimes. We can see your screen.
Okay. Yeah. Okay. Yeah. So just super big picture.
Maura.
Yeah.
It just stopped.
Okay. Yeah, it's kind of weird. I've had this problem before on my Mac, and I'm not sure why. Like when I go into slideshow mode, then it stops sharing. So I'm just gonna leave it like this. Is that okay? It's fine. Yeah, I'm just gonna leave it like this. I need to figure out why it does that, but I don't have time right now. Yeah, so unless Megan, do you want to share your screen? Like, do you have it up?
I could try it. Yeah, sure.
Because we're kind of going back and forth anyway. So if yours works, maybe you could try it and step through. Because I don't know.
Yeah, sure. I can try.
I don't know what my problem is with Google Slides.
There's always something weird.
Well, it happened to me the other day too. When I tried to do Google Slides and go into the full slideshow mode, then it just
Does that
doesn't
work?
share anymore. That's great. Okay, cool.
Wait, okay.
So I'll do the first couple, and then Megan will take over. Yeah. So just for those of you who might be new to NANOGrav, I wanted to like just step back and give a super big picture overview about the IPTA. So the IPTA is the International Pulsar Timing Array, and this collaboration was formed around the same time as NANOGrav. Initially, it consisted of the EPTA, that's the European Pulsar Timing Array, NANOGrav, and the PPTA in Australia. Recently, the Indian PTA has also joined. And the MPTA, or the MeerTime PTA, using the Meerkat telescope in South Africa, has recently signed a data sharing agreement. And that phrasing is intentional. They are not a PTA collaboration like we are. They have members from kind of all PTAs, but there is an African Pulsar Timing Group, or the APT collaboration, that is looking to become an official IPTA member in the same sense as the EPTA, NANOGrav, and NPTA and PPTA. So a group of people localized in South Africa, training students kind of with like local resources. The next DR3 data set, as you heard from Deborah, will contain all the recently published data sets plus Meerkat data, CHIME data, and LOFAR data. So it'll be way more sensitive than previous data sets. And I think Deborah did a really good job of explaining like why we want to do this. These international combined data sets are much more sensitive than individual PTA data sets. as long as they can be produced on a time scale that's not too much longer than the individual PTA data sets. Can we move on to the next slide? Yeah, so just a little bit more just about like procedural stuff, information about the IPTA. If you are not familiar with the IPTA, there is a website, ipta4gw.org, and there is an internal tab on that website where you can access the IPTA wiki. You do need a username and password to do that, but you can easily sign up for a username and password. You can go there and see all this good stuff. So there are membership policies, authorship policies, data sharing policies. There's information on different committees, working groups, you can get involved in, papers, meetings, things like that. NANOGrav has provided a lot of support for the IPTA over the years. And in fact, the first NANOGrav funding we had was from a program called PIRE, and it was actually for international research and education. And we currently have some funding from an NSF program called ExcelNet, and that is funding Euros for Beast as our project manager, and Kevin Wilson, who's doing providing computing resources, and it's also providing a whole bunch of hardware for IPTA data storage and data analysis. It's funding a planetarium outreach show as well, which is pretty cool. We've also had a lot of student exchanges supported by the NSF, which has pushed IPTA science forward. And just a little bit about IPTA accomplishments since it was formed. So in the time since the IPTA was started, there have been 2 data releases. The first one had 49 pulsars. The next one had 65. They included data from 7 telescopes. The collaboration has grown to include the Indian pulsar timing array and data from mirror time. And of course, the major achievement of the IPTA over the past year has been this coordinated process, which resulted in gravitational wave detections, evidence discovery, whatever you're going to call it, from PTAs worldwide of a stochastic background. So this was really exciting. And this plot on the bottom left is from a paper that Paul Baker led, comparing the spectral properties for the data from the different PTAs. And the little screenshot on the right is all of the different papers that went up on the archive at the same time from all of the different PTA collaborations. And that took a huge amount of work and coordination. And we are in particular grateful to Sarah and Deborah for all of their efforts that resulted in this process being successful and happening.
Excuse me for one sec. Okay, so I think Maura gave a really good overview of what the IPTA has been up to over the years. Right now, as you already heard this afternoon or this morning, depending where you are, from Deborah, the IPTA third data release, DR3, is in progress. This, when completed, will have 115 MSPs from 10 different telescopes, data from 115 MSPs from 10 telescopes. And a 20 pulsar early DR3 has already been created. On the right here, you can see just a snapshot of those combined data for those 20 pulsars. And once this full data set is complete and has been analyzed, we expect that this should give us a significant detection of the gravitational wave background. Oh, and of course, the figure on the left here is showing locations of those pulsars. Okay, so we've been talking about the MPTA quite a bit lately. Their first data release has already been, actually, no, I guess it's public. I mean, it's going to be given to, well, yeah, it's public. It's right there. Sorry, I should know this. And the plan was for this data release to be included in DR3. They're currently in the process of putting together their second data release. And they're at the stage of checking their noise modeling right now. And so I don't know exactly where this stands, but there's at least been some discussion about putting this data from the second MPTA data set into the IPTA DR3. I don't know that that's been decided one way or the other, but it's at least a possibility. Regardless, whichever data set goes into DR3, it will certainly be very helpful for making this detection. So I think back to you, Maura.
Okay, great. Yeah, so we're now kind of moving from like the overview bit to discussion, and we have a few questions that we'd like to discuss. But maybe before we move on to the questions, are there any questions right now about sort of like IPTA history, organization, the process, like accomplishments up to this point? Okay. So we have a few questions to discuss, and we'll try to moderate things so we get done, at the right time. One of the first things we thought we'd bring up is whether we should be trying to coordinate observing strategies better worldwide. So currently, all of the PTAs carry out their own independent observing programs. There are some pulsars in common, like a lot of pulsars are in common actually between, say, us and the EPTA. The PPTA, because they're in the Southern Hemisphere, has a little bit less overlap, but there's still a bunch of pulsars that we observe and they also observe. And we're kind of getting into like a very interesting time, right? Where these are some plots. The left plot is something that was shown in Jeremy's talk. The upper plot is a plot from a paper by Ting Liu, which shows that if you want to detect continuous wave sources, you do much better with a shorter cadence observations. But for the stochastic background, you kind of want different things. And Jeremy already talked about this a bunch, so I'm not going to go into this in detail. But, do we want to tune like our observational program along with those of the other PTAs to either hit kind of more independent pulsars? We could drop some of our pulsars that are observed by other PTAs and observe the ones we're observing now with a higher cadence or for longer, for instance. So I think I'll stop there and just leave this and see what people think. Does anyone have any thoughts about this? Natalia.
Yeah, I just have a question because I'm aware that when we are actually paying for our observing time, the other PTAs don't do this necessarily. So they are as far as I know, they are basically submitting proposals for this. So is this actually feasible from that point of view to coordinate with them? I mean, every observatory has its time constraints and so on and so on. So have you ever discussed this with the other PTAs, like concretely how this would look like?
We really haven't. I mean, I think there might be some like very nascent discussions at IPTA meetings. I think it'd be a really fun project and I think there has been some work done on this. I think Andrea Lohman did some work on this, like optimizing a global IPTA. And Michael Lamb has done some work on this for NANOGrav, like sort of simulating like individual pulsars, tweaking the PTA. And we don't even really do this for NANOGrav that much, right? Like we could even tweak our own program a lot with observing different pulsars for different amounts of time, right? We kind of, yeah, thanks, Steve. We kind of just kind of stick to our default program because it's what we've been doing. It's simple and it's pretty good, actually. I don't think we're going to do a lot better by tweaking things. But I don't know that it's like the bought. I don't know. I don't know if like the purchased versus competitive time is really what makes a difference.
Yeah, I was just curious if you have gotten any input from the other PTAs on that yet, because I'm not claiming to be in their shoes, but they know how scheduling observatories work.
I mean, EPTA does this, right? They do a mini version of this all the time with LEAP, I think.
Okay.
Yeah. No, I think it was Steve and then Thankful.
Yeah, thanks a lot, Maura. So you mentioned that this plot here shows that going to weekly cadence helps a lot with continuous wave signal significance, but I'm not really seeing that from this plot. The line does go up, and there's some gain and be a slight reduction in that fractional frequency recovery, but
yeah,
it's not dramatic. Yeah.
I mean, it's going, signal to noise is going up by a couple, and the fractional error on the spectral index like goes, it decreases by maybe a factor of, I don't know, it decreases by 30% or something. These are mostly up here just like for eye candy, just to be honest, like these are not meant to be super strong selling points for coordinating observations. It's just sort of to show that people have looked into different observational strategies for different types of sources, and should we be discussing this kind of optimization IPTA wide? But yeah,
I suppose part of it is, studying optimization does require us to make some bets on, rough locations of where a single source might be, and if there's a strategy that allows us to hedge our bets a little bit and create an overall optimization that keeps track of things we might not totally expect, then that might be the best thing. Just so we don't go all in on something that ultimately steers us in the wrong direction.
yeah. And my guess is what we're doing now is probably pretty close to that. Like, it's probably pretty close to a hedging our bet strategy. I don't know. Thankfully, did you put your hand down?
Yeah, I put it down.
Okay. David? Well, actually, let me go to Ting Ting first, because I think Ting Ting might want to talk specifically about this plot, which I might have massacred the explanation at. So
no, that's okay, Maura. We did this for a few injected sources. So S1 is one of them, may not be the best example. So there's I usually show S2 or S3. So if people look up in the original paper, they will see there are few different versions of this, and that might address Steve's question of whether improvement is significant.
Thank you, Ting Ting. David.
Yeah, so I want to agree very much with what you said, Maura, that what we're doing seems to be working. And I think there are two important points. One that Steve made is hedging our bets. If something goes wrong somewhere, Arecibo collapses. We've somehow survived that, but that sort of really dramatic thing happens, then we want other telescopes in the world to be able to pick up the pieces there. And I think having redundancy is really important. I also think that redundancy was super important with our announcements last summer. It was really nice that we kind of independently did our own thing, and then there were similar results seen by other PTAs, basically consistent with one another. And having those things be quasi-independent, I think, is really reassuring to all of us. It's reassuring when we all see 1713 doing the same quirky thing, that it's not just our data set or our telescope, but that it really is the pulsar and or the interstellar medium in between us and the pulsar. So I feel like even if we were to coordinate a little bit more with the IPTA, having a lot of redundancy where the same pulsar is observed by a lot of different telescopes is really useful, even though it's a complete pain when one is doing data combination. Well, that's all I wanted to say.
Thank you, David. Yeah, and we have a lot of topics for discussion and really not enough time to bring any of them to fruition. So I think we should probably move on to the next topic. Megan, am I covering this topic too?
Yeah, but either way is fine. I think you do this one and I do the next two.
Yeah, sure. So one thing which has come up recently, and this was brought up by Sarah Burke-Spillar. She sent an email to Megan and I and has much more well-defined ideas about what a continuous wave detection task force would do, kind of a list of questions that a task force would look at. But one thing that has come up recently is whether we need to put together like a kind of cross PTA group for continuous wave detections. So I think the stochastic background process was a little difficult because by the time we had started talking to other PTAs about criteria for detection, by the time we started talking to them about like, a kind of a checklist, what we would like to see in a bona fide stochastic background detection, we already had a signal. And so it was kind of politically difficult, right? If we don't have a continuous wave detection yet, at least I don't think so. And so it seems like a good time to maybe think about putting together like a cross PTA task force, nothing as formal as the detection committee that you know, was made for this stochastic background, you know, more like a group that just thinks about like how to assess significance, how to do parameter estimation, how to associate continuous wave candidates with electromagnetic sources, things like that. It seems like the right time to do that. So we just wanted to bring this up and see what people thought about this. And I see Steve and then Sarah.
Yeah, I really agree with this, Maura. I think the fact that we don't have a promising continuous wave signal yet makes this the best time to actually organize this when there's no tension and heightened feelings about things. But we did have something like what you're suggesting within NANOGrav for the gravitational wave background. We had this 15-year study group that Michaela Valesneri chaired. And I think something that's across different PTAs that's like that, it's a scientific study group, rather than it being anything like the IPTA detection committee is the way to go. Keep it focused on the science and present it as just a study or a memo to the IPTA community, rather than it being anything that is imposing requirements on the IPTA. I really agree with this, yeah.
Yeah, I like that idea too. We weren't thinking of something like people would sign or like say, we definitely agree with this. And we're specifically using task force instead of committee. So people don't get the idea this is different. Sarah?
Yeah, I think this is a great idea. And I also think that the timing is right. I mean, I agree with everything Steve said, but the other thing I wanted to add to it is that compared to the gravitational wave background, there isn't as much literature on continuous wave significance and background estimation. And so I think there is considerable work that needs to be done, which is another reason why I think we need to start as soon as possible. I think this is going to be very challenging, but very interesting. And you know, we really need to be prepared to dig into this because, you know, I do think it's very likely, well, the first signals that we see are going to be low significance, and it's going to be hard to know what it is. And also, I think it's, you know, well, we know that these searches do tend to pick up stuff that goes away in other data sets. And so it's presumably caused by some noise. And so the question of noise modeling and background estimation and exactly what models we should be comparing, I mean, these are going to be tricky to sort out.
Yeah, thanks, Sarah. Yeah, and I feel like there's this whole other aspect, right, of like individual sources and does this particular individual source make sense, you know, like in a way that's different than with the stochastic background, because we actually have electromagnetic observations of galaxies and things. So I think it'd be really interesting to put this together. Yeah, any other thoughts about this? Okay, we should probably move on, but I think this was useful. And of course, if people have thoughts about this after this little brief thing, just relay them to Megan and I.
Okay, thanks everyone. So the next topic is how to make the IPTA more cohesive. And we've come up with a few ideas. We'd really like to hear other ideas from you, as well as what you think of these ideas, how we might go about them. So the things we've been thinking about are, should we have some all IPTA telecons? Certainly not monthly, maybe something like every 3 months. Thinking about how to have more exchanges between you know, all levels of members, students, postdocs, and faculty, as well as more engagement kind of between leadership and more junior members. We're thinking of more engagement with you know, early career researchers, so grad students, postdocs, young, you know, early faculty. So yeah, we just wanted to see if people have thoughts on this. First of all, is it needed? And secondly, if you have any ideas that we haven't already thought of. And I can't see hands. So if someone, either Maura or Sophia, could field questions, that'd be great.
Looks like Natalia has her hand up.
Okay.
So perhaps on what Deborah just said in the chat, that many times when it comes to the IPTA, I thought, let's make the world flat. Would be the easiest thing to do.
Yeah, let's work on that.
I think it would be really helpful to have these quarterly all IPTA telecons. Because it's kind of like hard to see what people are actually working on. We are all working on many different things, and I think communication is key. And it would also, I don't know, probably when we have these quarterly all IPTA telecons, the exchanges between students and postdocs, what is your second point, would probably be a little bit induced by that. So, and I would like to think what the other PTAs are currently working on. You know, it's hard to keep an overview from the outside. I would say it's almost impossible to do this. So more engagement with junior IPTA members, definitely. My question is just, and I think I asked Joris this question a long time ago, do we have actually an overview of how many junior members are coming in, going out, and stuff like this? I think I had this question based on the IPTA website for him. So under other ideas, very quickly, I would just like to add that these hack days that we have within NANOGrav are actually super helpful to get together. And again, I know that since the world is not flat, it would be hard to have something like this for, IPTA wide, but it would be definitely, I think it would be helpful, especially for junior IPTA members, to kind of like not only get to know each other, but also to start working together across the PTAs. So I'm pro all of the suggestions that you have here, and adding this kind of like hack day idea to the other ideas. Thanks.
Okay, thanks. I guess naively, I think of a hack day as like, getting together to work on specific projects. Could be data combination, could be other IPTA projects. Is that kind of what you're thinking as well? Okay, thanks.
Working together across the PTAs. I think the data combination part that Deborah is leading, that's actually quite a good eye opener on how this can work. She's the expert, so.
Speaking of which, Deborah has a question too.
No, I have a comment. So one of the things I think would be helpful in the IPTA would be a little more clarity, and this is not, necessarily not necessarily easy to do, but I think one thing that's challenging for junior personnel at the IPTA is that it's kind of unclear how to join. It's kind of unclear what you're allowed to do and not allowed to do. And I think we've seen some of this play out just already today, with people asking, what do I do to make something an IPTA project? How do I get involved in an IPTA project? So I think one thing that might be helpful would be a written down somewhere thing about how to get involved in an IPTA project or how to propose an IPTA project, so that supervisors and students and postdocs feel like they can say, I want to work on X. Is anyone working on X? How would I go about working on X? So that there's a little bit more ability to do it. I mean, there's a bit of a leap of faith aspect, because we've had conversations in the past about how, supervisors are rightfully and reasonably reluctant to put students on IPTA projects because of the level of, the intensity of politics that can happen alongside the IPTA. But some of the only way we can make that improve is by people taking a jump and saying, one of my students' projects for their thesis is going to be this IPTA thing. And I think, the smart play is to say, you're going to have 3 projects one for each of your chapters, and 1 project will be IPTA related. So if it totally falls apart, there's still ways to get around it. But I think, I think one of the ways that things get healthier is you get a broad range of people involved. And I also think one of the things that is hard for me, and I think hard for a lot of people, one of the ways we make the IPTA more cohesive is by coming in with humility and assuming that we might be wrong. A lot of, I think, how we can make the IPTA better is in changing how we interact with one another and how we approach questions, and coming in with an attitude that prioritizes listening and hearing what other people are doing and why they're doing it, rather than assuming that whatever we're doing is correct. And look, we're all gonna, you can still have your sidebar conversation with your friends where you're like, oh my gosh, I can't believe how such and such PTA is doing this and that. But in an IPTA meeting, it goes a long way to be like, to come in with an aura of curiosity and of humility to say, you know, what are you doing and why are you doing it? And how did you decide to do that? Because it may just be that we're doing something stupid and or something not as good, and they've come up with something that's a really positive option. So I think, you know, those are a couple of my thoughts.
Yeah, it's a very good points. Thanks a lot. To your point about student projects, I'll just say quickly, so the GWA working group has been thinking a lot, and other working groups maybe as well, about you know, kind of the balance between protecting student projects, but also if the student is working on something that a lot of people might want to work on, or something that's really essential to the IPTA, how to deal with that. And if Nihan is on, he can correct me if I say anything wrong, but something we talked about in, I think it was 2 steering committee meetings ago, they had kind of come up with, you know, it's okay to have multiple people working on a project as long as you know the student is going to have this in their thesis. But it might be something that where duplication is useful, right? You know, like scientifically important to have more than one person doing the same thing. And there might also be things that need to be done on shorter timescales for the IPTA, like an IPTA priority. And so we don't think that should necessarily mean that a student can't also have that work in their thesis. They might be doing things a slightly different way or something. So I don't know if that completely goes to your point, but I did want to mention it because I think it's important. You know, I think it's an important consideration for students and their advisors when thinking about, do you want to do an IPTA project or not? Like, and the other thing is to start listing contributions in IPTA papers the way that we do in NANOGrav. So I'm hoping that will at least be somewhat helpful in getting more people interested in doing at least part of their thesis on IPTA data or IPTA projects. But I like your idea as well, kind of like a cheat sheet or something, like, okay, you're new to working in the IPTA, here's how to get involved. I really like that idea. So thanks for that.
I'll just doubly interject. I've also been recently soliciting people from a variety of different contexts and time zones about how they want to learn about new processes. And one of the things I've heard a lot is that people do like a written document more so than necessarily a call or a tutorial or something like that they'd have to watch or attend. That there's a nice, that people actually do like a nice written tutorial.
Yeah, that makes sense. Yeah, thanks. I don't know if there are other thoughts. It's because I can't see hands.
There are no hands so far, some comments in the chat, no questions.
Okay. I guess, are any of the comments in the chat things that people want to speak up about, or should we move on to the next topic? Let's see, we have 7 minutes remaining. Everyone's favorite topic with a slight twist. Instead of should we go all in or not, maybe we should think about what are the reasons that we might want to go all in? And when we talk about all in, I think we're talking about, you know, having a real shift in where our focus lies. So instead of having so much focus on individual, like not individual, but like NANOGrav only data sets and analyzing those data sets and then going to the IPTA from there, instead kind of letting, you know, a large part of the NANOGrav only work go by the wayside and instead be really focused on full IPTA data and analysis. We talked about this, you know, before, you know, when Maura, to get credit, she primarily put these slides together. We were talking about, you know, should we even discuss this topic? And I think a lot of the times we talk about it, it just gets very frustrating for everybody. So maybe we could think about, are there, you know, certain conditions that if met, then we would want to kind of switch gears and start to have, you know, much more of our focus on the full IPTA as opposed to NANOGrav only work. So if people have thoughts about this, also, you know, please feel free to raise your concerns with going all in and also your reasons why you want to go all in. It doesn't have to have this very narrow focus, but we did want to also make sure to, at least think a little bit about, some criteria for deciding when, if and when we do want to go all in. So any thoughts on this?
We have some raised hands. First was Ross.
Yeah, I wanted to say that I think from my perspective, to go all in on IPTA data sets, we would need to have a place for people to work on methods development and also secondary science more at the IPTA level. I think it's like a significant barrier right now that the IPTA data sharing agreements say we can only use this data for pulsar timing array science for gravitational waves, right? So that means certain things that we might want to do with the data are off limits. And I think, to me, that's a big barrier for going all in.
I definitely agree with you. I think if we were to make this decision, we would need to, make some pretty big changes to rules like that.
Next, we have Steve.
Thanks. Yeah, I think in order to justify going all in, there would need to be an unequivocal demonstration that the IPTA produces better science. And I don't know, I think if we're honest with ourselves, we haven't seen that yet. It should, it really should, and it does in simulations. But I can't think of something that unambiguously shows that yet. Hopefully DR3 does. And then I also think we'll always be beholden to how we're funded. And as long as we're funded as a large collaboration with one of these large grants by the NSF or some other body, we'll have to show what we've done with the funding we've been given within a reasonable timescale. And if IPTA combinations in science gets quicker, maybe that's possible. But if things lag beyond what we can do individually, then that creates a kind of a difficult situation. And it makes total sense that we will have to justify to the people paying us what we've done with the data collected. So those are just two pragmatic thoughts.
Thanks for that.
Okay, cool. And last we have Nihan.
Yeah, I agree with what Ross and Steve have said, and I'm more of an optimist than Steve. So I do think DR3 is going to end up being better than even NGXX, and we'll see how that unfolds in the next few years. But even if that does happen to be the case, I think there's still some room for us to do our PTA-specific analyses, even from a detection standpoint, where one of the sort of cross-validation techniques that we have to do is split up the whole PTA into chunks and see if the signal still exists in all of them, or do these self-consistency checks. And I don't see any reason why that couldn't happen at the individual PTA level. So there's still some room for individual PTA analyses to still happen, even if sort of the big flagship numbers are coming from a fully combined IPTA dataset. So it doesn't have to be a one or the other thing. I think we can all just live peacefully together.
Yeah, I've heard that before as well. So I think this is kind of coming from, my understanding is that GWIC really wants the IPTA to just be one big thing as opposed to individual collaborations, and maybe someone can say whether or not that's truly the case. But I think that's at least part of why this keeps coming up. Thanks a lot for those comments. Are there any other thoughts on this?
We should be finishing soon at 5:10, and by soon I mean now. So any last minute questions, concerns, comments?
Okay, great.
I think the thought that we should all live peacefully together is a great way to end that session and the day. Thank you to Maura and Megan and Sophia. We'll pick up again at noon Eastern, 9 a.m. Pacific tomorrow for day 2. Thank you, everyone, for your participation, and we'll talk tomorrow.